Hi, welcome students. Myself, Dr. C. SIVA here from the Department of Physics and Nanotechnology, SRM Institute of Science and Technology, Chennai. Roles of optical computing. We'll see certain roles which optics can actually play, which cannot be actually executed by electronics, or the superior power of optics, we can say in other way, both in terms of qualitative as well as quantitative. Let's consider array mapping, 2D array mapping. See, parallelly, we can actually process the data with the optics very easily. Let's consider lambda 1, lambda 2, lambda 3 in a array and row based. Okay, sorry, column and row based. Okay, so uh, let's consider lambda 1, lambda 2, lambda n. Okay, lambda n. At the same time, it goes up to lambda n here. Okay, and it continues. Okay, lambda n comma n. In this, we can see like a massive, massive parallel arrangement of light pulses, which can be actually transmitted, which can be actually operated with devices. Let's consider transversers, which do the operations and simultaneously which gives the output also. When we have the n cross n input means n weighted interconnections. Okay. Such a function can serve as the backbone of a truly massive parallel neural network or fuzzy programmable logic array. It can also implement 2D to 2D mapping. 2D to 2D mapping. A number of data which is actually available in 2D array can be actually mapped into n number of data in 2D term. Whether or not that mapping is 1 to 1. We can actually map in any aspects. Optics can handle n on the order of 256 now itself to provide parallel weighted interconnections. Providing such interconnections electrically, if we are trying, okay, it would actually lead to the confusion of the wires with strong, strongly we will actually get confused with that. Okay, if we have a continuous function that changes continuously with the time, sampling can be used to represent such a function. But we can never achieve time continuous transformation, time continuous transformation and time continuous signals with the digital technology. But with optical, we can actually achieve that. Second one is garbage free operations. In a traditional Turing computer, a physical device must perform each operation. Each device operation consumes uh, time and energy and is subject to error. If we could make a system which can actually tackle all of the steps in terms of actually measuring the device operations, it would actually save the corresponding amount of time. Let's take any computational steps. Without following all those steps, we are actually ending up with a easy way, like a Vedic mathematics or some other way. We are actually ending up with the proper answer. So like that way, if we could actually make it, okay, we are saving the time, energy as well as cost. Some optical processes can achieve this, but the price we have to actually pay, which we cannot actually easily know because the unmeasured operations. Garbage bits or information we generate while we do the operations in to produce the desired answer. But we really do not need to know their values. Okay, as an example, if we need to know the sum of the first six integers, we add 1 to 2 to get 3, and then we would add 3 to 3 to get 6, and so on. All the intermediate sums are garbage. In optics, it is often the case that we do not measure the garbage terms. We do not save those things also. There are no possibilities. Fourier filtering actually multiplies each pixel of the Fourier transformer of the input pattern with a pixel from the mask and then uses a lens to sum those products. We never measure even one of those products or even one of the partial sums. We never measure even one of those products or even one of the partial sums. We can correctly say that an optical processor performs intermediate steps virtually. We can easily say optical processor performs the intermediate steps virtually. And virtual events carry no price, not in speed, energy, error, or money. So we are saving so many things. The next one is the other topic, next topic, optical computing paradigms. Hmm. Optical computing paradigms can enhance conventional computing methodology and at the same time it remain hidden from the end user. The systems can be actually attached to the electronic host, any electronic devices, and it can undertake certain operations which called subset, and it is relieving the host, which is electronic host, from a corresponding computational load, because the corresponding computational load will be actually taken responsibility by means of the optical computing paradigm. Keeping a new technology hidden from the end user is an important factor in the technology acceptance. If novel architectures are introduced seamlessly, users will adopt them without a fear of tearing down their established investments. Hmm. See, if the novel architectures are introduced seamlessly, users will adopt them without any fear of tearing down, which um, can actually give a negative ends. Okay. Some of the optical computing paradigms are analog optical computing, digital optical processing, analog digital hybrid optical computing, analog optical processing, which entertains analog operations on set of analog data, such as continuous time pictures, real time images obtained by camera lens, or light beams modulated by analog electronic signals. Analog optical processing entails analog operations on set of analog data such as continuous time pictures, real-time images obtained by means of camera lens, or light beams modulated by analog electronic signals. Let's consider an input device which is being developed uh, to communicate with us. For example, with the finger movements, if you are actually trying to give any calculations, if it could actually able to understand and it is actually processing based on the same, those kinds we can actually utilize. We can understand as an example for this kind of analog optical processing and tests. The functionality of analog optical processing is unique to optics. Its advantages have laid the foundation for the early success systems. The functionality of analog optical processing is unique to optics. It Its advantages have laid the foundations for the early success of optic systems. Okay, students, with this we can actually stop this lecture. We'll see the next topic in the next video. Thank you. Sorry, students, let's continue this. Okay, we'll wind up only this small part. Digital optical processing, the use of light to perform digital logic targets, a class of applications that are currently performed by electronic computers and can be enhanced by optoelectronic architectures. The ability of multiple optical beams to propagate in free space. Multiple optical beams, let's consider red, green, yellow, blue, violet, all together. A multiple optical beams to propagate in a free space with a minimal interaction among them led to attempts to replace wires with optical links. The logic next step was the development of all optical or optoelectronic switch techniques in an effort to replace electronics functionality and take advantage of free space optics. Digital analog optical processing involves hybrid techniques and systems that can process both type of data, both type of data in the sense digital as well as analog. This paradigm may be better suited for optoelectronic architectures than electronic ones. Electronic associated systems tend to be costly and are usually limited in terms of size and speed. Furthermore, they are incapable of handling analog data such as images or time signals. Thank you, students. We'll see the other topics in the next video lectures. Thank you.